Meeting is being recorded.
Good morning, everyone. Good afternoon, good evening, wherever you are joining from. My name is Lindsay Floriance, and I'm an associate scientist here at Pumas AI, and we are so glad that you are here to join us for today's webinar, which is first order methods for non-Gaussian nonlinear mixed effects models in Pumas. Next slide, please. Here at Pumas AI, if you're not familiar, we engineer solutions that empower people from discovery to delivery. We have two main products, the first one being Pumas, which is a back-end analytical engine that focuses on clinical pharmacology workflows from early NCA to NLMEs to optimal design to machine learning. And it drives our second product, which is Live, and it is a clinical decision support system being used in hospitals currently. And if you'd like more information about that, you can always contact us at sales@pumas.ai. Next slide, please. So today we're going to focus on Pumas AI, which is our accelerated drug development software. The goal with Pumas, of course, is to accelerate any drug development you have within your current pipeline, but we are also committed to providing the best user experience possible. So next slide. And these are just a few of the things in summary that we can do. We are currently validated against other industry softwares. We are an all-in-one software. We're also accepted by the US FDA for submission. We're also super fast, which is something you'll see today. And in the future, we're working on machine learning applications. Next slide. So as of April 2022, we are currently running Pumas 2.1, which if you were able to join us last year, we released Pumas 2.0, which was our first feature series. Next slide. And so today, this webinar is part of our current Pumas feature series, which can be found at Pumas Lab at our website, where we will upload this recording and our code from today as well. Next slide. So today, I'm joined by Dr. Andreas Nowak, who is our Director of Engineering Research here at Pumas AI, and is also the Director of Research at Julia Computing. He's been a longtime contributor to the Julia ecosystem, and we are glad to have him. We are also joined by Dr. Jose Staropoli, who is our lead of training and education. He's well known for his book on Julia data science and YouTube teachings involving data science, statistics, Bayesian statistics, machine learning, and deep learning in Julia R, Python, and Stan. So with that, I will hand this webinar over to them.
Hello, here's Andreas Nowak. I'll start out giving an introduction of the material here and what we plan to cover, and go through a little bit about how we formulate error models in Pumas in general. And then I'll talk about the scope of using the FOC approximation in Pumas. The scope is a bit broader than you'll typically see in other software solutions. And I'll briefly give an overview of that before giving some more details about why the FOC approximation actually makes sense in a broader class of models than just the additive Gaussian case. Then once I've completed that, we'll shift over to my colleague, Jose, who will be giving a live demo of demonstrating how this can be used in practice. So first, the Laplace approximation is based on a second order approximation of the log likelihood function. That's kind of how it's generally defined, and specifically how I'll refer to it here. But the difference between the Laplace I approximation and the FOC approximation is in what kind of approximation you use for the second order term. So when you do a quadratic approximation, you have some freedom in choosing the second order term. And depending on the choice of that second order term, it will either be called the FOC approximation in Pumas or the Laplace approximation. But it is essentially both the Laplace approximation. So don't be fooled by the name that one of them is called Laplace. They are both based on the Laplace, the integral approximation called the Laplace approximation. The advantage with using the FOCE version of the approximation is that it only requires first order derivatives. So instead of having second order derivatives, as is usually the case for a Hessian matrix, the FOCE approximation of the second order term is based out of an outer product of gradients. That is much cheaper to compute in terms of floating point operations on your computer, and it's also softer or cheaper in terms of compilation. So in both senses, you will experience a faster evaluation of your code if you use the FOC approximations over the Laplace I approximation. The two approaches are asymptotically equivalent. So for a sufficient number of data points in the time dimension, they will give you the same result. So this only matters in finite sample, but of course, in reality, samples are finite, so you will experience a difference in real applications. But eventually, as the number of sample points in the time dimension grow, you will or you should experience that the results become exactly identical because they approach the same limit. So historically, the FOCE approximation has been associated just with Gaussian models in pharmacometrics. Outside of pharmacometrics, the Laplace approximation has been used more broadly, but the Gaussian models have become very popular and are completely dominating the field of pharmacometrics for various reasons. I believe this is to a large extent associated with the software development, where the Gaussian models were made available in a very convenient way early on in the available software packages for pharmacometrics. And therefore, people got used to modeling their data through Gaussian models. However, the Laplace approximation works beyond just the Gaussian setting, and it's also possible to use the Hessian-based Laplace approximation to non-Gaussian models in most software packages, but it requires more coding of the user typically, whereas the Gaussian case is special handled and made and it's often supported by special syntax and therefore easier to use. So here we'll extend the FOCE case or show how the FOCE case in Pumas is extended beyond the Gaussian case to the generalized linear type error models and the typical extended class of generalized linear models. So a brief overview over the history here. Very selected overview of the history, but in pharmacometrics, you can trace the Laplace approximation back to Wolfinger in '93, where it was suggested for the first time, as far as I know. And then in a slightly different setting, it was also treated and analyzed in Pinheiro and Bates in '95. Beal and Scheiner introduced it in non-MEM in the fourth version of this software package, and it's then described in the manual there in '98 and named FOCE there. In the previous treatments in Wolfinger and Pinheiro Bates, it's labeled the Laplace approximation, and there's some differences in which approximation for the second order term I mentioned before is being used in the two approaches. But the specific version based on the simplified Hessian is named FOCE in non-MEM user guide version 4. There was still a little bit uncertainty about the exact objective function and how the relationship was between linearization approaches. So when you linearize the nonlinear regression function with respect to random effects, and then the Laplace approximation, there was then a need for clarification because of that, and the paper by Yanning Wang in 2007 gave this clarification. So it explains how linearization is related to the Laplace approximation in the additive Gaussian case. In particular, it describes how the objective functions in non-mem are actually, or the mathematical description of the objective function in non-mem. So there are various software packages that support these kind of models, mixed effect models with various Laplace approximation methods. So of course, there are the R packages and NMLE and LME4, which were based off the original theoretical work by Benignium Bates and written by the same authors. Then SAS has long time support for these kind of models in various procedures. In Julia, we have a package for covering the traditional linear and generalized linear mixed effects models, which is written by Douglas Bates, who originally implemented the R packages, but now works in Julia. And then, of course, there's the PUMAS package, which we offer, which has support for specific support for dynamical system in the model, which is kind of the special feature that is required by pharmacometrics analysis. Then, of course, there's non-mem and others. So let's talk a little bit about how you specify error models in PUMAS. So in some other software solutions, you might have a special casing of the Gaussian case, particularly if you consider non-mem. There, the standard setup is for the Gaussian case, and there you formulate your model in a regression-like setting. So the Gaussian error model is closely related to nonlinear regression models. So you can write the model in a typical regression style where you formulate the conditional mean, and then you write some epsilon, which is then representing a Gaussian distribution and therefore telling you that it is a Gaussian model that you're working with. But if you go beyond Gaussian, then you need to formulate your error model slightly differently. So that's what the approach we have taken in PUMAS. So instead of using a nonlinear regression style formulation, you specify what is the conditional distribution of your data given the random effects. That's how you specify it. So there are examples here, 5 different. So in PUMAS, you specify the error model distribution in the derived block. And here the variable being modeled is y, and tilde is then used kind of similar to how you do in normal probability, that it tells that y is now following a distribution. So I have also, together with the different PUMAS notations, shown the mathematical moment properties here, so the conditional mean and variances, because they're important for various reasons. They're important because often when you look at some data, you will try to kind of eyeball what kind of moment properties will the data have. You'll consider which value can the data take, and then also kind of roughly how does the mean and variance, what is the functional relationship between the mean and the variance. So that's why for the different distributions here, I've shown the mean and the variance. So the classical reference is the Gaussian additive case, where you have a conditional mean of y, which is equal to some model value. Here we just call it mu, and then you have a variance which is independent of the mean. So that's the traditional approach when you consider these models, because it's the easiest one to analyze. And it's also, as we'll talk about later, that's the case where linearization of the nonlinear regression models is exactly identical to the Laplace approximation using a certain choice of the second order term. However, for pharmacometric data, or in particular pharmacokinetic data, you often don't experience that the standard deviation is the same for large means and small means. It's common to experience that the larger the mean is, the larger the standard deviation of the data is. Hence, it's common to use a distribution where you have the property that the variance of your data grows proportionally to the mean of the data. And that is the case for the proportional Gaussian case, as you can see to the upper right here. So that's, I'm showing the variance, so that's the squared version, but the standard deviation, there you have a direct proportionality between the standard deviation of y, conditional on eta, and then the mean mu. You can get something similar if you model your data in log transformed, or which is equivalent by saying or specifying that your data is log normal distributed. So that's in the middle to the left here. So in PUMAS, you can simply write that y is log normal, and that will be exactly identical to log transforming your data and then modeling the log transform data. In this case, you don't have the exact equality. So for instance, neither in the mean nor the variance, but for small values of the variability sigma, there you will have that they're very close. So the expectation of the y given eta is almost mu if sigma is small, and the variance is almost, or the standard deviation is almost proportional if, again, if sigma is small. In the generalized linear model literature, it's often the gamma model that is preferred for this kind of data. So in the traditional reference for these kind of models, McCulloch and Melder, they propose using the gamma model in that situation. So it has the property that, as we discussed before, that the standard deviation grows proportionally to the mean. You can then see that in this parameterization here with nu, that it is inversely related to the sigma variance parameter from the proportional Gaussian model up here. But otherwise, the relationship is the same. You have this proportionality property between the standard deviation of y and the mean parameter mu. The gamma distribution is a bit nicer than the proportional Gaussian, which can be exported in various ways, and it is the reason why we can cover it with the FOC approximation, as I'll show later. But there's various other advantages with using the gamma, so it is something you can consider doing in PUMAS, which might be slightly more complicated in other solutions. Finally, I've taken an example of a non-continuous random variable. Here, the Bernoulli distribution, which is the distribution used if you're doing a logistic regression, where you then have, again, a conditional mean equal mu, and then you have a variance, which is the product of mu and 1 minus mu, just to show that there is essentially no difference in how the model is specified between the logistic regression case and the Gaussian case. So that's how error models are specified in PUMAS. So here's a overview of the scope, and we can return to this slide once we have gone through a bit more theory. But a way to think about the various models that are covered by different approximations is with a figure like this. So we have kind of 3 circles, and then you can see with the small letters, or the words with the small letters, they are different kind of error models. So you have center, truncated, time to event out here, then Poisson, gamma, proportional Gaussian, and then in the inner circle here you have the additive Gaussian as a very special case. So the very special inner circle here, you have the additive Gaussian case where you have where you can linearize a nonlinear regression function. That will then be overlapping with the FOC approach here. Then you have a broader set of models that can be handled with the FOC approximation. which is gamma, Poisson, binomial, categorical, proportional, and the combined Gaussian. That class of model is related to or similar to the generalized linear model kind of distributions, but also a few more, right? So categorical and the proportional Gaussian, for instance, they are not typical, or they are not GLM models, but they can be handled similarly to those. And then finally, there are a couple of models that are not covered by FOCE because they have a too complicated likelihood function, which I'll return to later. But that'll be the models for incomplete data, censored and truncated, and also time to event model, which generally won't be possible to handle in the FOCE framework. So I'll return to this slide here later, and then we can revisit. Now let's talk a bit about the theory and why the FOCE approach can be extended to models typically not considered feasible for FOCE. To do that, we'll write down the model so it's clear what we're talking about. So we'll start out in the additive Gaussian case where we have a direct relationship between linearization of the regression function and the FOCE case. So we'll have data here called Y. We have I and J. So we have a subject dimension and a time dimension, which is then a mean mu, which is a function of population parameters theta, individual specific random effects eta, and some covariates xij, which will not be important for this treatment, but for completion they are included here. And then there's an additive idiosyncratic error epsilon ij, which is not depending on anything. So it is a additive case or the homoscedastic case, which is sometimes called the statistics. Since we're not interested really here in the covariates and initially not so much in the population parameters, we abbreviate the mean to a mu ij, which is then just a function of eta, because that's the interest here. We'll figure out how to get rid of that eta or integrate out that eta. The eta is a multivariate Gaussian in this simplified case here, and the epsilons are independent, identically distributed Gaussians as well with the same variance as mentioned. And theta is the parameters of interest, and x can be a vector, but again, it doesn't matter for this treatment. So there are two routes to FOCE. One is through linearization, and one is through the Laplace approximation. We'll analyze each, as did Wang in his 2007 paper. First, let's consider the linearization approach. So in the abbreviated form, we can write again y equals mu of eta as a function of eta plus epsilon. So this is in vectorized form. So here y only has one subscript. It's now a vector where all the time elements over j have simply been stacked on top of each other. So mu I is in the same way a vector, and so is epsilon I. Each of these will be a vector with all the time observations stacked on top of each other. We can now linearize this expression around the mode, so the empirical base estimates, as they are also sometimes called, for the random effects. So that's the point where the gradient of the log likelihood will be 0 in at least in cases where the model is well behaved. So we'll have the constant term mu I in eta star, and then we have a Jacobian term j, which is the derivative of mu, the mean, the conditional mean, I should say, with respect to the random effects, times eta I minus eta star, and then finally epsilon. So this is a first order approximation of the model in the top. And in this first order approximation, of course, the random effect eta I is now entering linearly. So this is a linear random effects model, at least with, when talking about the random effects. A different way of saying that, so you can say it's a regression model where eta enters linearly, and also epsilon enters linearly. So a different way of saying that is that yi is approximately a multivariate normal distribution with mean ui evaluated in eta star minus a correction term of the mean j eta star r, j eta star I, and then there is a variance term which has two terms, or variance component that has two terms. There's one from the kind of the idiosyncratic part with sigma times the identity here, and then there's a part coming from the random effects which contains the Jacobians and then the variance covariance matrix of the random effects. But just to state it again, this way of this regression style formulation of the model is equivalent to saying that yi is normally distributed like this. These two formulations are equivalent. This model here has it's a Gaussian model now, or approximated with the Gaussian model. So we can write down the Gaussian likelihood. So this is the typical Gaussian density, log density, with the specific choices of means and variances from the first equation here. We'll return to this one shortly, but this is just to show this is how the likelihood contribution for subject I looks like. The other route that can be taken is, instead of linearizing the regression model, we can look directly at the likelihood function, the real likelihood function of the original model. So the model where the random effect enters nonlinear in the mean, conditional mean. So that likelihood function will look like this. That integrates out the random effects, but usually this integral is not tractable, and therefore it has to be approximated in one way or the other. So the traditional approach in pharmacometrics is then to use the Laplace approximation. There could be other approaches, but the Laplace approximation is convenient, and it's typically very fast. It can then be shown that the Laplace approximation will look like this. So you'll make a second order approximation of the log likelihood. So the Li theta eta I up here, a quadratic approximation of that around eta star, which means that the first order term will disappear because the gradient is 0. And then there'll be a W here, which is the coefficient on the quadratic term in that second order approximation. And finally, there is the conditional likelihood evaluated at the mode here as the first part. So then the question is, how should W be chosen? It can be chosen again as the actual Hessian of the joint likelihood, log likelihood function up here, or it can be a simplified version. Before diving more into that, let's note that the linearized version, so if you go back 2 slides here, so this version here, if we use 2 results from linear algebra, the Woodbury matrix identity and the determinant lemon, then we can rewrite it in this form here instead. So we can get it in a form where we again have the conditional log likelihood evaluated in the EBEs first. Then we have this term related to the normalization factor of the Gaussian density. And then finally, we have a log determinant here, which is omega inverse plus sigma to the power of -2. And then this kind of end up in a product of the Jacobians. So compare this equation here, the linearized version of the likelihood function to the version here coming from the direct Laplace approximation, where we have an arbitrary choice W of the quadratic term in the Laplace approximation. So it's clear that if we choose this W term from the Laplace approximation to be equal to omega inverse plus sigma to the power of -2 j transpose j, then the two equations are exactly identical. So that shows that the linearization approach and the Laplace approximation approach are exactly identical for this specific choice of W here in the middle of the screen. So they are not generally equivalent. They are only equivalent if W is chosen in a very special way. But given that choice, they are exactly the same. Now let's go back to Yanning Wang's paper in 2007, where he introduces the W as the conditional expectation of the Hessian conditional on the random effects being equal to the EBEs or eta star. There he shows that you can split that up. So you can split up the joint log likelihood into the conditional and then the penalty. So from the penalty term, you'll get the omega inverse, and then you'll have the expectation of the conditional log likelihood here, which he then shows or argues can be written as the condition of the outer product of the gradients of the conditional log likelihoods. So the advantage here is that certainly this is an expression of gradients instead of involving Hessians. So instead of having second order terms, it will only need first order terms. And if we then revisit the gradient for the conditional log likelihood in the Gaussian error model case, then we'll get exactly that it is sigma to the power of -2 j transpose j. So here it's clear that the expectation of the Hessian of the joint log likelihood, where we condition on the random effects being equal to the EBEs, will end up being that specific value of the W that is required to have equivalence between the linearization approach and the Laplace approximation approach. To hint to how this extends beyond the Gaussian case, let's try to take a look at the log likelihood of a non-Gaussian model. So here we consider the Bernoulli case. So we say that the conditional distribution of Yij given eta I equal to the EB is a Bernoulli distribution with a mean mu ij, which is then a function of eta in general, but here specifically evaluated in the EBEs because we condition on the random effects being equal to eta star. The conditional log likelihood here can be written out, and the gradient of that expression can be written up like this with three factors. So there's a first factor, which is the derivative of the mean with respect to the random effects. Then there's a central factor here, which is 1 over something that you might recall is the variance of a Bernoulli distributed random variable. And then finally, there's a difference here between the observations and the mean. So that's the three factors here. If we write that on matrix vector form, we'll get that we have a Jacobian term that's stacking all the derivatives together. Then we'll have a diagonal matrix of the variances inverse, so one over the individual variances. And then finally we have the vectors of observations minus the vector of means here. So if we compute the outer product of these gradients and take the expectation, then we'll get an expression that is J transpose, or the Jacobian transposed, then we'll get a diagonal matrix with all the variance terms of Y, and then again a J. If we look back here, you can see it's actually the same thing we have here. We have sigma squared, 1 over sigma squared, so that could also be put in the middle here, but they happen to be the same for all diagonal elements, so we can put them outside J transpose J. So the structure of this expectation of the outer product of the gradients here is exactly the same. We have a Jacobian, so the derivative of the mean with respect to random effects. We have something related to the conditional variance of the observations given the random effects evaluated at eta star, and then again the Jacobians. That's a general structure. So as long as we can compute the variance, conditional variance of our error model distribution, and we can compute the Jacobian of the mean function with respect to the random effects, then we can use the FOC approximation. That's the takeaway here. So your software solution will need to compute these two quantities, and if it's able to do that, then the FOC approximation can be used as a way of approximating the likelihood. This means that the software solution would need to understand the specific choice of distribution, because if you specify a Gaussian case, a Gaussian error model, then we need to compute one approximation here of the Hessian, but these can be in a language like Julia, which Pumas is based on. There's good support of offering different variance computations depending on the distributions. So we have implemented for each distribution mentioned earlier calculations of these different quantities here, which is what makes it possible to use the FOC approximation to evaluate or approximate the likelihood. With that, I will stop. I'll briefly revisit this slide here again, because so all the distributions that will have this nice structure that I just mentioned, where you can compute the expectation of the Hessian just as a function of the Jacobian of the mean and the variance of the error model, that's what's covered by this light blue circle here. And the reason why the sensor, the truncated and the time to event models are then not included is that they will not allow for such a nice structure where the Hessian simplifies to just an inner product, a weighted inner product like the one I showed you before. With that, I'll hand it over to the live demo, which Jose will handle.
Sure, and also folks, feel free to ask questions in the chat. If you have some theoretical questions about what has just been exposed, feel free to ask now, or we also have questions alongside with the code in the end of our presentation. So I'll share my screen. So I think I need to share the whole screen. So I'm going to do that. Otherwise, I don't have audio. Okay, let me move this over there. And can you see my screen and can you hear me? Okay, thank you. And we had questions here. Okay, thank you. So this is our, and feel free to interrupt me, my colleagues, because I'm only seeing my screen. So this is our Julia Hub. This is Pumas in the cloud, a very easy and convenient way to use Pumas. I'm I'm having some issues with my browser, so this terminal font is not being rendered, but if I highlight it, it's rendered okay, so bear with me, please. I'm just gonna show you a simple example. Then I'm gonna show you something more interesting with simulations. The simple example is a PK model with ordinal regression inside. It's let me just execute some packages here, and this is a model that we have categorical. This is the likelihood function. It returns categorical uh, probability likelihood, and it's based on probabilities of several categorical values. Here we are using 11 values. So we need 10, k minus 1, 10 different intercepts because of the equidistance assumption of the categorical, that the categorical regression or the ordinal regression violates. So this is just calculating the log cumulative odds, and then we convert that back to probabilities with the logistic function, and we put them, we convert back to cumulative probabilities. Then we just take uh, probabilities by undoing the cumulative nature, and then we put everything in a categorical vector here. So this is our likelihood function for this model. We are this is a big ordinal model, and we are just using this to showcase that both approaches for estimation methods, as Andreas pointed out, are equivalent, both the Laplace I and the FOC, and also show how one could be much faster than the other and giving similar results. So this is our model. We have typical values for everything. We have random facts. We have some data here, some fixed effects, and our random effects here. We also have two covariates, and this is our and our model is has an analytical closed form solution, which is a two compartment oral model. We have a central one and peripheral one, and as you can see here, our variable y, the pk part of y has a normal Gaussian likelihood, and the PD part of y has a categorical or ordinal or logit ordinal, depending on where you are coming from, likelihood. So we just generate some. Our data is synthetic, is a simulation. I'm just gonna set a seed, and I'm also generating random covariates here. My sample times is this vector here that spans from time 0 to time 8. And I have several dosage regimens for those sample times. So this is the population for all of those dosage regimens. And I concatenate all of that population into a single population called POP, and I then generate observations. I simulate the data based on my model and that population, and also the initial parameters from my model that I specified above. And then I convert the simulated data set into a population by using the subject constructor vectorized, so applied element-wise. And this is the part that we fit our model. So I'm going to call first FOCE, and I want you to pay attention in my terminal, because the evaluation, the iterative evaluations of the model of the log likelihood will pop up, and it should be a little bit faster once the model compiles. And when I run the Laplace I, you see that the iteration will be much slower, because it's a more costly estimation method, as Andreas pointed out. And since I'm using a categorical likelihood, I can use FOCE. So if you remember the slides with the ellipsis curves, the like of the onion slides that Andreas just showed, um, at a categorical likelihood, I can approximate as an inner product of the Jacobian. So it's a first order approximation. As you can see, it's really fast. It's like maybe 1 second per iteration. And our model will converge, and here's the time. The time is down here. So it will converge, let me see, in 24 seconds. So this is the final time. Oops. So here is the final time that it converged, 24 seconds. So now let's do the same for the Laplace I. It's the same thing that I'm calling. It's just that I'm using a different estimation method as the fourth positional argument here in my fit. So let's run this. So the FOCE, it's pretty much a first order approximation. I just compute the inner product of the Jacobian matrix. And for the Laplace I have to have the full Hessian. So it's way more costly every iteration. And we are going to see it in the optimization trace that will pop up in our terminal in just a bit. Now it's as you can see, the evaluation is still fast, but not as fast as the FLCE as before. And this might maybe be twice slower than the FOCE. Let's take a look. I think it will converge around iteration 40 or something like this, so a couple more seconds. As you can see, this model is twice, is way slower. Mostly twice slower than the FOCE. So our total time of optimization was 51 seconds. And if we compare the estimates, let me just push and give more real estate for the tables. So let me just compare the estimates of both models. And you can see that they are pretty much, let me highlight this, they are pretty much very similar. They are pretty much the same. So they are very similar. So similar estimations, similar maximum likelihood estimates, but one runs half the time and the other one runs double the time. So this is what I wanted to show, and this is a big model to showcase this estimation difference in time. Now I want to show another example. This is this is a FOC. This is a logistic regression model. And for this, I used let me zoom in a little bit. I think it's better. Yeah. I used Julia hub or Puma's IDE Julia Hub to run this code in a cluster. I'm not going to do this now because this takes 3 to 4 minutes to run, but I can pretty much start a distributed process. I can put like 96 CPUs, and I can also select like 100 nodes. So then I can have like 10,000 machines running my code if I want to, and I can just pick up a Puma's image options, and then I can run, and then I can fetch the results. So it's really easy to do that in Puma's cloud. I already have run this, so it's in this result here, and I can easily uh, grab the code here, and I can pretty much copy the path because I don't need to download this code here, and I can copy, and I can pretty much use this file here. So let me explain this simulation. This is a simple logistic regression model where we have four fixed effects data, and we have omega between subjected variability matrix, which the values are small because it's zero point 0.1, so we don't have a lot of influence of the between subject variability. We have four covariates for those four thetas for fixed effects, where we compute the thetas here, where it's our theta 1, theta 2, theta 3 to 4. We added the etas, the between subject variability. We have a linear predictor here, and this linear predictor is being fed to a logistic transformation, and then we condition our we use our dependent variable y is conditioned. It has a likelihood, a Bernoulli likelihood. So since those terms they enter linear in the likelihood in the transformation, we can use an FOCE here, estimation method, as Andrea explained it. And this is pretty much a function to simulate the data. And we are using data for all of those four, the vector of 4, 1, 2, 3, 4. So our data goes from 1 to 4. And then we do an FOCE, a Laplace one, and we concatenate those two data frames, and we return the results. And I do a parallel map here, and then I simply serialize the results. I save it in a serialized manner, which is pretty much like the save RDS or R data if you come from R, or if you come from Python, it's similar to the Pico module, where you can save binary files from your objects. And here is the nice part. So I'm going to deserialize those results. I'm going to just filter out the fail ones, because if it fails, it will return a missing. So I'm pretty much just grabbing everything, vertically concatenate all of those data frames, and then filter. But before that, filtering out the missing values. And this is our true values. So I'm just interested in the parameters that are as the keys in this dictionary. So just interested in theta 1, theta 2, theta 3, theta 4. And I'm generating histograms of the distributions of the estimators for each sample size and estimation method. I generated for 4 sample size, 10, 20, 40, and 8. It was 200 simulations for each sample size and for each estimation method, Laplace I and FOCE. And here I'm calculating deviation. I'm calculating uh, what is the estimate from the model, from the estimation run, and the true values from this dictionary here. And I'm computing a deviation where I scale this difference for the by the square root of the sample size. And I'm going to be plotting some results here, and let me grab more room for you. Now, let me close this. The plots will come up shortly. Uh, do we have any questions in the chat? I think we can begin to start take questions now once the plotting is done. Oh, I need to. Yeah, I had some errors because I haven't defined uh, some things before. I forgot to run. So we can start taking questions. Feel free to either type in the chat or open your mic and speak the questions. Uh, we have one question. Is there any free PK models to buy? I don't understand this question, sorry, but uh, if you are an academic, Pumas is free to use for academic purpose, but otherwise you can contact us at sales.pumas.ai. We do have analytical solutions for lots of models, or you can specify your own ODE. If you go into docs.pumas.ai, and I'm gonna zone in here, and you click here and you go uh, I always forget where is it. Analytical solutions of differential equations. So you do have several analytical solutions. So you have one compartment model, you have one compartment auto model. So you have several analytical solutions, but you can also specify your own ODE system here if you want to. These solutions, they have a closed form solution, so the models are much faster because it's a simple matrix exponential. It's linear, so it will only do a matrix exponential. So let me show you the plots, and I'll go back to questions. So the first plot is just the FOCE. So here are the histograms, and as you can see, the rows are the sample size. So to our left in the rows, each row is a sample size beginning from the top. We have 10, 20, 48 in the bottom, and each column is a parameter. So as you can see, uh, the deviation, it gets narrower when your sample size increases. It's more clustered around zero, because the deviation being zero, that means that our the estimate is closer to the true simulated parameter value. This is for the FOCE now, and this is for the Laplace I. And the Laplace I is something really interesting happens because uh, we have some numerical instabilities, and those they kind of are more rare when you go into a larger sample size. But since our sample size is small, we have some outliers here that pull the parameter values towards crazy numbers like 500, 1,000, and pretty much this is the product of 200 simulations. So each one of those subplots is 200 simulations. So here you can see that the Laplace I suffers from some numerical instabilities in some of the runs, not all. And of course, the estimation is much slower than the FOC. And here is just the Laplace I. Sorry, no, this is okay. So this I'm using data limits -10 to 20. So here is just the Laplace I, but with the histograms focused on without the outliers. So as you can see, the estimation is pretty much similar to the FOC. And finally, these are Laplace I and against FOC, and let us put the data limits here for a good comparison. So these are the data limits are pretty much limited to -10 and 20. So here is FOC and here is Laplace for the sample sizes and as you can see, when we remove the outliers runs that generated some crazy parameter estimates, this estimation methods, FOC and Laplace I, they are pretty much equivalent, with the Laplace I having some numerical instabilities in some of the runs. So let's go to questions. So let me take questions now about the code or about the theoretical mathematical explanation from Andreas. And let me stop sharing my screen.
Doesn't look like there are any questions.
Yeah, and I dropped it. My browser crashed when I started sharing the screen.
I'll just comment that the original motivation for extending the FOC to a broader class of models was to get the speed benefit. But as you said, simulations they showed, it looks like there might also be numerical advantages from using FOCE over Laplace I for smaller sample sizes, which is kind of an interesting result. So they definitely look like there might be some small sample improvements to be gained from using FOC over Laplace I, which would be useful or interesting to analyze more.
And also one more thing, I see some mention in the chat from folks being really looking forward to learn Pumas. We do have free onboarding sessions to teams, either academic teams or commercial teams. So feel free to contact us at sales@pumas.ai. And if you are from academia and you have a research team that wants to use Pumas, we can provide free onboarding and training for you. And also, if you are a commercial user and you want to buy, evaluate Pumas, we also provide how many onboard sessions you need for you and for your team.
Well, since there are no more questions, thank you everyone for attending. The slides and code will be posted to Pumas Labs on our website under the summer series 2022, which you can find under tutorials on Pumas Labs. We will be having another webinar in 2 weeks at the same time on handling truncated and censored data in Pumas if you're interested. The registration link will also be sent in an email containing the link to Pumas Labs later this week to you. So with that, we will stick around if there are any more questions, but otherwise have a good morning, good afternoon, or good evening.